Okay, so today we're going to be proving the fundamental theorem of algebra, and that is the statement that if you take a polynomial over complex coefficients, and of course we need the polynomial to be non-constant, so degree at least 1, the highest term is non-zero, then that polynomial has a root in C. And then of course by dividing out those roots we can show it has exactly capital N roots with multiplicity. So it's a fundamental theorem. It's pretty important, obviously. And what's a shame is that most textbooks in complex analysis will only show you really hard proofs, right? They'll be, by hard, I mean it's a proof that requires like Liouville's theorem or some algebraic topology or some kind of heavy machinery. And there's actually a pretty simple proof that only uses very fundamental facts. So I wanted to show you that simple, just bare bones proof, because for a fundamental theorem, it really should have a fundamental proof. And it does have one, so here it is. This is the list of facts that you need to prove this theorem that aren't just like basic arithmetic or stuff about modulus with complex numbers. So just to go over them, you need to know that you can rebase the polynomial. And maybe this is obvious, but just following the same as argument as the real case, you can rebase at any complex number z naught. So just take the polynomial above, plug in z equals z minus z naught plus z naught, that doesn't change it, and then if you just FOIL that out, you collect all the z minus z naught terms, and then the z naught to the n terms will all get pushed into the constant. So you can rebase polynomials. Here, of course, you have the triangle inequality and the reverse triangle inequality, and if this is the first time studying complex numbers, then you probably should sit down and convince yourself of these. But again, it's the kind of thing where the actual formal proof doesn't give you much intuition. The picture is really all you need to convince yourself this is true. And then this follows from a clever usage of this. You need to know the map from z to its modulus is continuous. And again, this kind of follows from the definitions. It's not hard to think about or check. This fact gets a star because it is not something that's easy to sit down and prove if you've never ever seen it before. So we want to know that every continuous function on a closed and bounded set has a global minimum and also a global maximum, but we only need the global min part. And this is the extreme value theorem. If you've taken multivariable calculus, this probably was stated as a fact for you to accept. The proofs that I know require you to do a little topology and kind of show that closed and bounded sets are the same as compact sets, at least in like R2 or C. And then once you have that, it's a very easy proof to show that a continuous function on a compact set has extreme values. But otherwise, just from bare bones, no machinery required, this is the highest level fact you need. And the rest, you need to know that the map from theta to cos theta plus I sine theta is surjective onto the unit circle. And of course, this is obvious from cos theta being x, sine theta being y, so it's surjective. And then you need de Moivre's formula. And again, I'm trying to avoid any hard facts or tricky things to prove about complex numbers. This you prove by induction on n, just using some trig identities. And you take this with the above fact to get that the map theta from cos theta plus I sine theta is also surjective, right? You just divide whatever theta up here, you just divide it by n, and then it'll work for the map down here. So that's surjective onto the unit circle. And then some notation, we need to know that cosine theta plus I sine theta, we need some good notation for that, so I'm using e to the I theta. Of course, this has more meaning than just notation, but to give this a proper meaning and really justify what I'm writing down here, you need a whole theory of power series for complex numbers, which is also something you do at the beginning of the class, but now we're getting into more machinery here. So for now, this will just be notation. And again, for people new to complex analysis, this is 1, then e to the I theta is this point here. And you can scale this by r to get any complex number in the plane, and you can write them all of the form r e to the I theta. So it's a very powerful characterization. And then z to the n is r to the n e I theta to the n. So you take the magnitude, the modulus, and raise it to the nth power. And then you take whatever angle theta is and you multiply that theta by n. So that's how you exponentiate a complex number to some natural power. So these are all the facts you need about complex numbers. Other than the extreme value theorem, they're very basic kind of fundamental facts that are easy to cover, easy to convince yourself are true. And this is all you need to prove the fundamental theorem of algebra. So first we need a lemma. And we're going to prove that for any polynomial, non-constant, the limit as the magnitude of z goes to infinity of p of z is infinity. So in other words, as you take z of larger and larger magnitude, eventually this magnitude of the polynomial will grow to infinity. So this is not the most formal statement right here, but you can kind of get what I mean. So the proof, what we're going to do is we're going to use the reverse triangle inequality. This is greater than or equal to magnitude of a to the n z to the n minus all of the rest. And then we're going to, let's just move that around like this. We're going to use the regular triangle inequality here, but it's negative, so the absolute value still works the way we want. And then if z is bigger than 1 in magnitude, then the largest z to the n can be is at z to the capital N minus 1. Okay, and now we're going to factor some stuff out. And let's just call this alpha. So alpha is this thing. And this is strictly greater than 0 because we assume that it's non-constant. Well, actually I guess we don't know that. We just know it's greater than or equal to 0, but whatever. So we have some term here, and then a sub n is non-zero. So we can pull that out like this. And then this is either 1 if capital N equals 1, or it's some power of z, so that equals 1, or goes to infinity as magnitude of z goes to infinity. This here is non-zero, because we assume the highest term is non-zero, or else there'd be no point writing it. And this also goes to infinity as magnitude of z goes to infinity. So we bounded p of z magnitude below by something that goes to infinity, and so p of z goes to infinity as z goes to infinity. And that is the end of the proof of the lemma. Okay, so now we're going to move on to the proof of the theorem. And down here we don't have much space, so I'll just sketch the idea. So the idea is to argue, using the lemma, that, I should say, if p of z is never 0, then p of z in magnitude has a global min of mu greater than 0. And this is not too hard to argue. It's going to use the lemma above. And then we're going to contradict this. basically if f of z naught, or excuse me, not fp, if p of z naught achieves that minimum, then the picture is like this. We have some minimum mu, p of z naught is here, maybe z naught is here, and p is mapping here to here. And if you think about how complex numbers work, if I take a little ball around z naught, p should be mapping that little ball somewhere around p of z naught. And maybe it's wiggly, or because of high powers it's like, flying around in circles. But if you look at the picture, we say, oh well, look at this, there should be some point on the ball that gets mapped to something closer to the origin. But that's not right, because mu should have been the global minimum. So that'll be a contradiction, and then we must have a root after all. So that's the idea of the proof, and that we're going to do on the next page. So we have a new page. So continuing the proof of the theorem, what we're going to do is we're going to claim that p of z has a global minimum mu greater than 0. And actually first, I'm going to suppose for contradiction that p of z is never 0. So for all z, p of z is non-zero. Assume that, we're going to get a contradiction. So suppose, or we're going to claim that this has a global minimum in magnitude. So first, by the lemma, there exists some r, such that whenever z is bigger than size r, the polynomial has size bigger than 1. And this is all we needed from the lemma. The polynomial, of course, goes to infinity. We just need to bound it away from 0 for large enough z. Then by the extreme value theorem, this function, so the function z maps to the magnitude of p of z. This is a composite of continuous functions, so it's continuous. This function is continuous, so this has a global minimum, call it mu naught, on the ball of radius r. So these are all points, distance at most r, away from the origin. So away from r, we have that the polynomial has size greater than 1. On the ball around the origin, this is a closed and bounded set, so it has some global minimum mu naught, strictly greater than 0, because we're assuming p of z is never 0, around the origin. So on c, the magnitude of p of z is greater than or equal to the minimum of 1 and mu naught. Either outside the ball, then you're bounded below by 1, or you're inside the ball, and then you're bounded below by mu naught. So this is what we call mu, and that's strictly positive. So we have some global minimum. We're going to show a contradiction by showing this is actually not the global minimum. So let z naught have p of z naught equals mu in magnitude. So choose some value that realizes that global minimum. And now we're going to consider what happens when you plug in the points z naught plus epsilon e to the I theta. So here epsilon is some small positive real number. We're taking z naught and we're moving in a little circle around it of radius epsilon controlled by theta. So we rebase the polynomial at z naught. And then we note, because we said the degree was capital N, I believe we're going to use this at some point, but we note that b sub n is non-zero. And we also need for b not to be non-zero as well. Maybe not, but we'll see. Point is, both of these are non-zero, and we'll use them if we use them. So now we're going to try to bound this above, and if we could bound it above by something less than mu for some choice of epsilon and theta, then we're done, because that choice will have length less than mu, and that contradicts mu being a global minimum. So we're going to first take off b sub k. So I'll write it down, then I'll say what I did. We're going to take off some value b sub k. Excuse me, I wanted to plug in this point. So we plug in this point, which makes it all epsilon e to the I theta inside this term here, because we take off the z naught. So we get epsilon e to the I theta to the k. Then we get the rest. And then we get b naught. And this is where k greater than 0 is least, such that b sub k is non-zero. So actually, here's a great place to use these two facts. So k greater than 0 exists with this property because b sub n is non-zero, and the least such value has to be greater than 0. So I guess we didn't need this fact, but well, the point is there's some k where these are 0, and maybe k is equal to n. So maybe this whole term here is 0, doesn't exist, but that's okay. The point is there's the smallest term, which is non-zero, the rest, and then everything else was 0 except for b naught. So we can split up the polynomial like this, and then we're going to use the triangle inequality. I'm going to stick that term, combine it with the b naught, plus the rest. Okay, and then we're going to use the triangle inequality there again. So we're going to have a whole bunch of bk's to the n. We're going to have epsilon to the n and e to the I theta to the n, but that has magnitude 1. So that actually goes away in magnitude. So we just have a bunch of epsilons to the n. And then we're going to define beta to be this. Oh, excuse me, I wrote k here. There's just an n. And we're going to assume that epsilon is less than 1, which means that the biggest term here is actually the first one raised to the power k plus 1. Of course, this might be 0, so if it is 0, then beta is 0, and it doesn't matter that we're factoring things out of nothing. So beta could be 0, in which case this makes sense. So it's just plus beta times epsilon to the k plus 1, regardless of whether or not k is equal to capital N. So this is the smallest, this is the largest the powers of epsilon can be, and then we have beta greater than or equal to 0. Okay, so the idea is we're going to choose theta now to put this complex number to the kth power, and maybe I should, factor the k inside. We're going to have e to the I theta k pointing in the opposite direction of b naught, and this is the key to the proof. So we choose theta such that e to the I theta k is equal to negative b naught over bk, and then I need to normalize this so that it has length 1. So we have b naught right here. This is negative b naught, or excuse me, divided by bk because it's in front. And then we're going to choose on our unit circle, choose e to the I theta k to be right there. And then when you add this to when you multiply by bk and add it to b naught, we move opposite direction of b naught over bk, and that will pull us closer to the origin. So that's the key here. So choose this theta, and we're going to use it. So I need a new piece of paper, but I'll restate this. So continuing the proof of the theorem, we had that the magnitude of this thing here is less than or equal to this thing here, where beta is greater than 0 and epsilon is less than 1. We still have control over epsilon. Beta is fixed. So greater than or equal to 0. Okay, so now we have that e to the I theta k is equal to this. So when I multiply by bk, we end up getting the following. It is going to be a little annoying to write down. So we get negative b naught epsilon k divided by this plus b naught k plus 1. And you know what? Let's just let rho be this number. It's some positive number. So b naught and bk are both non-zero. That is important for this. This is some positive number. So it's equal to, I'm going to pull out the magnitude of b naught, and then we get the magnitude of negative rho epsilon k plus 1 plus beta epsilon k plus 1. So rho is some positive number, beta is some positive number. This here is mu. Okay. Just make this a little nicer. So again, I'm just being very formal here because I want to leave nothing up to the imagination. We kind of saw the idea of the proof, so now we just need to play around with this and get this to be strictly less than mu. Because once this is less than mu, we're done. Because then this is strictly less than its supposed global minimum. So this here, right? Yeah, this here, rho is positive. For small enough epsilon, this is going to be less than 1. So we can choose epsilon as small as we want. So this is equal to mu. We can drop the absolute value. And now I'm going to factor a mu out of everything. Mu is non-zero, so I can do this. And then we're going to factor out this. And we get this here. So now this is less than 0 for small enough epsilon, because we have positive, positive, so just make this smaller in magnitude than rho. So that means this whole thing is less than 0. So this whole thing is less than 1. So this is strictly less than mu for small enough epsilon. And that's the end of the proof. So we chose theta so that this thing points in the opposite direction of b naught over bk, which was just something we had to formally figure out here. And then we chose epsilon to be small enough to make this whole thing less than 1. So the magnitude of p at this value is strictly less than mu, but that's a contradiction because mu is supposed to be the global minimum. So that's the end of the proof. P must have a root. And if you kind of think about what's happening here, we have a method now, kind of. If you have a supposed minimum of the polynomial, you can figure out epsilon and theta to give you a direction to move in to make this magnitude a little bit smaller. So it's not really constructive in a way because there's no guarantee that process is going to quickly lead you to zero or anything, but at least it's not like the worst non-constructive proof. For the record, every proof you see of the fundamental theorem of algebra is going to be non-constructive, but this has the benefit of being totally bare bones, no machinery required. So I hope you enjoyed.